Hey everyone, my name is Nick and I'm a master's student of software engineering at Western University working under Dr. Alexander Essex. In this video, I'm going to demonstrate an attack we carried out against a cryptographically secure internet voting system called Helios Voting. Before proceeding, I will let you know that after discovering the vulnerability, we contacted Ben from Helios and provided a fix which was deployed on May 30th, 2016. Helios is a cryptographically verifiable voting platform that allows anyone to host their own publicly verifiable election online. Helios has been used in multiple elections, claiming to have recorded over 100,000 votes. It has also been used by organizations such as the International Association for Cryptologic Research and the Bitcoin Foundation. Now that you have some idea of what Helios is, let's talk about the attack. Due to a small oversight in Helios' implementation, a dishonest election official can cast or allow voters to cast a nearly arbitrary number of votes for different candidates. So now let's take a look at how all of this happens. So right now we're looking at Helios, which is being served by a virtual machine running Ubuntu 16.04 and is being accessed by the host machine running Windows 10. I'm going to go ahead and set up the election as the dishonest election official. So right now I'm just entering details about the election name, deciding who's eligible to vote, and uploading my public key. This is where the small bug exists that will allow us to unfairly influence the election. First of all, we deviate from the default Helios behavior of letting Helios be the sole trustee by removing it and adding myself. I check my email for the link and I'm able to generate or upload a public key. Since Helios uses Elgamal encryption, the public key also defines the domain parameters. So as you can see here, we have a 2048-bit prime P, an order Q such that Q divides P-1, a generator G of order Q, and a public key Y, which equals G to the X mod P, where X is the secret key. Now that you can see the parameters, do you think anything's wrong with them? If not, don't worry. Helios doesn't think so either. We proceed by legitimately voting for Alice, after which Alice will log in and do the same. While that's happening, I'm going to speak a little more about voting in Helios. Helios uses the exponential variant of Elgamal encryption. This variant grants the property of homomorphic addition of ciphertext at the expense of having to compute the discrete log during decryption. This isn't a huge issue when the message space is small, like in this application. Ciphertexts take the form of a pair of group elements, alpha and beta, where alpha is G to the R mod P and beta is G to the M times Y to the R mod P. So a vote for Alice consists of two ciphertexts, the encryption of 1 for Alice and the encryption of 0 for Bob. For each of the ciphertexts, a Chom-Peterson proof is issued. This proof proves that the ciphertext encrypts either a 0 or a 1 and nothing else. However, as I previously mentioned, we were able to get Helios to accept encrypted values other than 1s and 0s, and we'll talk more about that in a bit. Now that Alice is done voting, we see Bob logging in, and Bob is my accomplice in this dishonest endeavor. While the election official can be the sole perpetrator of this attack, perhaps the official wants to maintain some kind of plausible deniability or distribute the responsibility. The idea is that for whatever reason, Bob is the only one casting the unfair ballot in this demonstration. So we can already see that he has the developer tools open where he has a slightly modified version of Helios' script used for client-side encryption. Notice the breakpoint on the right is where the script would return the ciphertext. This is how Bob is going to modify his vote options. Recall that a vote has a ciphertext for each option, and each ciphertext is a pair of group elements, alpha and beta. On the first break, i.e. the option for Alice, he's submitting the encryption of -1. After resuming execution, we wait for the breakpoint to trigger again. It's at this time that Bob is now submitting the votes for himself, where he's encrypting the value of 2. So you may be asking yourself, how does Bob defeat the proofs? Well, remember those parameters from earlier? The problem with them was that we had used a small value for Q, which was 647, and raised it to the power 27. So while the number looks large, it results in a subgroup GQ having small order of 647. We take advantage of this with a small modification to the script which loops until the real challenge for our ciphertext is congruent to 0 mod 647. Recall that in a Chang-Peterson proof, the verifier is checking whether the following statements are true, where A is G to the W, B is Y to the W, challenge and W are random elements mod Q, and response is W plus C times R. So let's substitute those values and see what we have. Now what happens if the challenge mod Q equals 0? The data that the proof is supposed to prove knowledge of is eliminated, leaving a trivial equivalence. So now let's look at the results of this election and see how it worked out. As we saw, Alice and I both casted legitimate ballots for Alice while Bob tried to do his own thing. We should expect to see at least 2 votes for Alice and learn of Bob's decision, but as we see, this is not the case. With the final tally being 2-1 in favor of Bob, we see that Bob was successful in not only casting 2 ballots for himself, but also in taking 1 away from Alice. Perhaps more interesting is when we go to audit the election tally, we see that Helios validates this incorrect result. This situation makes us believe that when evaluating the security of verifiable systems, it is also worth considering the risk of the audit itself, for it may act as a witness against fraudulent results. To wrap things up, Helios was not thoroughly validating the cryptographic properties of user-supplied parameters, and that slight oversight made this attack possible. We have fixed this bug, and we'd like to thank Helios again for their great work. For more information on this attack and others, see our AXAC paper, The Cloudier Side of Cryptographic End-to-End Verifiable Voting, a security analysis of Helios. Also, feel free to get in touch with any questions or comments, and thanks for watching.